Today I will be presenting on composites and metallic beams and stiffness and their deflection analysis. This topic is very important in aerospace and structural engineering because the choice of the material directly affect on the strength, weight and safety and effect on stress. Slide 2 agenda. First we are going to see introduction and objectives, then material properties and bending theory, and third we are going to see the case study of aircraft wingspan, and fourth advantages of advanced analyzing tools, then fifth innovation and ethical consideration, and sixth key takeaways and reference. Third slide, introduction and objective. In introduction and objective of the work of comparing metallic and composite beams in the term of stiffness and deflections, we will see how their material property affect on the performance and how engineers apply the theory in real aerospace structures, and ultimately aim to understand not just mechanical but also the design behind the metals and or composites. Slide 4 material property and bending theory. Let's start with the material property. Metallic beams are homogeneous and isotropic. Their modes are elastic and conservative, which make behavior predictable. They also have well-defined yield strength and fatigue limit. However, composite beams, are heterogeneous and isotropic. Their property is depend on the fiber and stickiness of the material. This means the engineers can customize the stiffness and strength, but analyzing become complex. The beam behavior is governed by the equation M by L by R. E is equal to R, E by R. For melt, E is constant. For composite, we use an effect of modulus which depend on the fiber and the material components. Fifth slide, bending, stiffness and deflection. Stiffness represent as E into I, the product of modulus and moment of inertia. For metal beam, E and I are fixed, so stiffness is straightforward to calculate. Means we can calculate easily stiffness in metallic beams. In composites, E effect is changed with the fiber, which makes the stiffness highly design dependent. Deflection is inversely proportional to the stiffness. Composite generally provide better specific stiffness, that is the better specific stiffness. This stiffness is relative to the weight, but poor design choice cause large deflection or strength condition, which can be dangerous in aerospace structure. This highly important to consider the both bending and shear deformation, especially sandwich type composites beam are used in aircraft. Slide 6, aircraft wing spar case study. Let's see how the application to real world in aerospace components are made. The aircraft wing spar are the main load bearing members transmit lift force across the wing. Traditionally, they are built from aluminium alloy. Metal are easy to design due to their nature is isotropic, but the highly density limited the weight reduced. We should keep the weight less for the aircraft. Today, many aircrafts use carbon fiber reinforced composites. They provide excellent stiffness to weight ratio, reduce the structural weight by 15 to 20% comparing to aluminium. However, the trends of the complexity, the composite design must be carefully considered by the fiber orientation, and the damage tolerant repair and inspection also became more challenging. Slide 7, advanced analysis tools. To ensure the reliability of engineering rely on advanced tools. Mohr circle allows visual to calculate the stress at the different orientation. This is especially important for composites, and off-axis stress occur by the By each finite element analysis, FEA divides the divides the structure into small elements and simulate in real world load, geometrical and material property. FSA is indivisible of the components. It predicts the deflection, stress, and the failure model, and that are difficult to calculate analytically. Towards these tools, we provide surety design validations. With this device, we can surely say the material is useful or not. Slide 8, Future Smart Composites. Looking ahead, composites are evolving into smart materials. Some key innovation include self-healing composite which repairs micro cracks and extend their life, integrating fiber optics for real-time structure, health monitoring, shape memory material which allows adapt structure, like the wing can change chamber in flight, energy harvesting component which converts vibration into electrical energy. This development shows the composites are no longer just passive structures, they are becoming intelligent and adaptive. Slide 9, Ethical Consideration. Material selection also comes as ethical responsibility. While composite reduce fuel compression and they are harder to recycle comparing to the material, life cycle assessment must be considered from raw material exhibition to end of the life decomposition. Engineers must also consider supply chain ethics, environmental impact, and all about safety. Thus, responsible engineering goes beyond the mechanical performance. It also includes social and environmental responsibility. Key takeaways to summarize. First point: there is no single best material choice. Depend on the application and loading condition. Composites offer super stiffness to weight ratio but require careful design. Tools like Mohr circle and FEA are essential for accurate analysis. Fourth point: future innovation and smart composite will be transforming aerospace design. Ethical and environmental factor must be selected as the material. Slide 11, Reference and closing. This work is supposed to be referred as Carter Material Science and Engineering Jones Mechanical and Composite Material and Server Aerospace Research paper. This conclusion of my PPT presentation. Thank you for attention, and I would like to end this PPT over here.